Okay, so if we go backwards in time and look for this picture and this equation together, it takes us directly past the Italians who we were looking at last time and back to our new friend Islamic algebra. Even though in their work we don't see the trappings of symbolic equations, the ideas of algebra, including the basic notion of an equation as a virtual balance, sort of this thing being the same as that thing, they emerge in this Islamic world between 800 and 1100 CE. It was here that this drawing above went from being a proof of a geometric fact, like it would be in Euclid's time in 300 BCE, to being a geometric proof of an algebraic fact or an arithmetic fact. So this relationship among arithmetic of numbers sort of stands on this turtle here. Scholars in the Islamic world put together Greek geometry, Babylonian arithmetic, and Hindu numerals and made them into something more. Like we saw last time with the invention of symbolic notation, with Hindu numerals it took a long time to go from whole numbers and their arithmetic to a fully capable system of arithmetic, although the Babylonians, far before this, had already developed a robust system of arithmetic with sexagesimal, in particular one where divisions could be carried out arbitrarily. As we look at some examples of these texts, it's worth remembering that we're also far enough back in time to be before Gutenberg's popularization of movable type and the resulting explosion in bookmaking. Original texts are harder to come by. Later copies are often transliterations. And as you might know, if you have some familiarity with, say, how the Christian Bible has changed over time, these transliterations are not just straight up copies of the original material. Often languages are changing, usage within languages change. It's not quite a straightforward thing to look back in time through these texts. But anyway, we'll start with Abu Hassan al-Khwarizmi, who wrote in Damascus in the year 952 CE, a book that extolled the virtues of Hindu numerals and described how to use them. The book was called Kitab al-Fusil fil Hisab al-Hindi, the book of chapters on Hindu arithmetic. And this book was the first recorded use of decimal fractions. Well, at least outside of China, but we'll get to that later. Even so, his use of division is halting. For example, he doesn't try to compute a decimal form for 14 divided by 3, and he only divides numbers by a small number of relatively simple divisors. By contrast, Al-Samawal ibn Yahya ibn Yahuda al-Maghribi, in his treatise on arithmetic in 1172 CE, shows that he fully understands decimal fractions in the context of approximation, even though he was still writing out numbers in words, which feels archaic to us, sort of far down the line of this decimal revolution. It's not until we get to Giha Thal Din Jamshid al-Kashi in the early 15th century CE that we first see both a total command of the idea of decimal fractions and a convenient notation for them. Though, as we've hinted at previously, that notation is still far from what we use today. When it comes to algebra itself, Islamic scholars picked up the notion of proof and the desire to explain not just how, but why from the Greek classics. So when it came to arithmetic and algebra, they had a model to use already, and they ended up basing their proofs of arithmetic and algebra on geometry, just like we did here. Another thing that distinguishes Islamic algebra from their Greek precursors is the attention to practical rather than theoretical matters. Euclid's geometry contains no direct measurements of either length, area, volume, or angles, other than right angles. And later scholars like Archimedes and Heron were not as averse to calculation as what we see in Euclid, but neither were the practical mathematical arts, things like surveying, astronomy, and the like, their first concern. Ptolemy's famous Almagest uses Babylonian sexagesimal numbers and invents chord measurements rather than relying entirely on Euclidean results to calculate the movements of celestial objects. There's a reason related to this discussion that likely explains why we know this title from its Arabic name, even though it's from the 2nd century and written by a Greek. Likely the most famous work of math that came out of the Islamic world is Al-Kitab al-Mutas Arfi Hisab al-Jabr wal-Muqabala, or the condensed book on the calculation of al-Jabr and al-Muqabala, by Muhammad ibn Musa al-Khwarizmi in 850 CE. We get the word algorithm from his name and the word algebra from his work. In the introduction, Al-Khwarizmi explains that the point of the book is to make more accessible, quote, what is easiest and most useful in arithmetic, such as men constantly require in cases of inheritance, legacies, partition, lawsuits, and trade, and in all their dealings with one another, or where the measuring of lands, the digging of canals, geometrical computation, and other objects of various sorts and kinds are concerned. Here's an excerpt of the math from Al-Khwarizmi's Algebra book, describing a similar idea to our drawing right there. Likewise, he used the illustration and geometric reference to prove the arithmetic case. Was this the first textbook where readers skipped past the proofs to get to the results? Now that we understand something more of the setting, we realize that in hoping to make sense of a school math class and its problems, other than the notation, we're in a pretty familiar place to the audience whom scholars like Al-Khwarizmi were writing for. And he didn't just have solace for things like a plus b squared equals a squared plus 2ab plus b squared. We can use the same idea of breaking up a square into parts to show that the quadratic formula really does solve the quadratic equation.